morning session of innovations in molybdenum catalysis, and thank you for being here. We're especially pleased today to have as our keynote speaker Dr. Phillip Mitchell from Reading University. Phillip is currently, and I have to read this, Liverwurm, right? Emeritus Fellow at Reading, as well as a reader in chemistry at Reading. But many of you, I'm sure, will remember Phillip as the man who organized those molybdenum chemistry conferences for many years back in the 70s and 80s, and did such a wonderful job of it. Today, Phillip is going to present an overview of what he's seen over the last several decades. I won't say how many decades that has been, Phillip, in molybdenum catalysis and where he sees it going in the future. Phillip.
All right, thank you very much, Carl. I prefer not to use a microphone if you know, one kind of gets tangled up in it. But if you can't hear me at the back, would you kind of gesticulate wildly, and I'll make a concession to modern technology. Bob. Carl, thank you for those kind words, and I'd like to thank the organisers for the invitation to come to the meeting in Toronto. And for those of you who are worrying about it, I should say I've already cast my vote in the British general election by post, so you know everything is in order. So, my theme is molybdenum chemistry, old and new. Now, I see the role of a keynote speaker as, okay, giving an overview, but trying to extract issues that other people might like to pick up. You know, I'd like to have a kind of 100 research students that I allocate each one to, but life is not like that. So I hope to bring out some of the issues and problems that you'd like to follow up. Now, I'm really an inorganic chemist fallen among catalyst people for many decades, and what interests me in chemistry is kind of looking at the patterns of chemical behavior. Now, in the past, these have tended to be kind of qualitative and empirical. I think the point is now being made that we want to get beyond this, because we've got density functional theory, which is the answer to the chemist's prayer. So I think one of the challenges is to relate all the kind of rules of thumb, all the empirical correlations, to the underlying theory which modern computers, modern computational methods allow us to do. And I think that in some ways is the challenge. And I think it's very critical what problems one selects to calculate. Well, so I'm going to expose the patterns in molybdenum chemistry. Now, the first point I want to make is that molybdenum is a pretty kind of sociable element. It's, some ways, the ideal free market element. It is essentially a captive consumer. You really don't get free molybdenum. As soon as you expose molybdenum to carbon, to nitrogen, to oxygen, to sulfur, so you're dealing with compounds, and this reflects the molybdenum binding strength, in contrast, for example, to the platinum group metals. So always we're dealing with compounds, and I think the challenge is kind of arranged marriages. You can't do anything about it. So that if we're dealing with carbon chemistry, we're dealing with carbide, nitrogen nitride, oxygen oxide, sulfur sulfide. It's inevitable. But we can fine-tune, we can introduce perhaps a little excitement, a kind of threesome, by adding a promoter or a dopant. And you'll see that the key to molybdenum catalysis is the role of the dopant. And that, I think a lot of our work is devoted to understanding that. So this is the fine-tuning. The other point that I want to make is, I think many of us will have attended Donna Blackman's plenary lecture, which, in fact, a fascinating and very brilliant piece of work. And she referred to the fourth dimension in catalysis. And this is really, I think, what interests me, the fourth dimension. Let's argue about structure. Exas will tell you anything you want to hear. And that's not altogether the point. What matters is reactivity. What I want to know is what's the structure that will do what we want to do. And this, I think, is where I would hope our calculations can be directed. Right then, so molybdenum, why don't we start with a little kind of undergraduate molybdenum chemistry? Well, group 6 of the periodic table, I think it's the most versatile of all the transition metals. Range of oxidation states, coordination numbers, very varied stereochemistry, polynuclear compounds. It can bind to most inorganic and organic ligands. The important point is that the energy differences between the oxidation states, between the coordination numbers, are small. I mean, we could quantify. And that means that the activation energy required for these interconversions are small. I think that's very important in molybdenum chemistry. Now, affinity for a range of donor atoms. Class A, in its higher oxidation states, oxygen donor ligands, but it's the first element in the transition metals that shows an appreciable affinity for sulfur. Molybdenum occurs as a sulfide, and the molybdo enzymes are molybdenum sulfur compounds. So the first significant appearance of metal sulfur chemistry. Go below lower oxidation states, and it's a class B acceptor, pi acceptor ligands. So that's what molybdenum chemistry is about, and what interests me, what I think is the challenge, is to see how that fits into the catalytic chemistry. Now, let me give two examples of what I mean by patterns. This is from some of the older literature. People I know very well, Moyes and Wells, who were then at Hull, looked at hydrogen deuterium exchange of benzene over metal film catalysts. As I understand it, this is one of the very few examples of catalysis by molybdenum metal, pure, unsullied molybdenum metal. And you'll see that when I say adapted, I converted the rates to moles rather than grams, and I resisted the urge to draw a straight line. And I shall return to the straight line theme at various points. But we can see the pattern of behaviour. Molybdenum is not bad as a metal, in terms of this kind of very fundamental chemistry. It's on the same level as platinum. Well, so that's a correlation with position in the periodic table. Well, what other correlations can we think about? Well, here's another one. This is the CO conversion over molybdenum catalysts, and this includes some work we did so long ago, long since forgotten, but I'm glad to see my colleague Robbie in the audience. We looked at CO conversion reactions over molybdenum carbon catalysts, molybdenum oxygen catalysts, and you say now then, and we've taken data from the literature, and you say now then, okay, CO conversion, what property of the partner atom are we going to try and relate that to? Oh, what shall we do? I thought, well, what about electronegativity and hardness? And very interesting, you see. The hardness, or some of you might be worrying, this is a bit old-fashioned, hardness and electronegativity. Let me reassure you, these drop out of density functional theory from the plot of energy against the number of electrons. Let me get let me not get diverted. But they're more respectable than you think. So, the electronegativity, well, as the ionicity of the bond decreases, so the ability to catalyze a CO conversion increases. Very nice. And similarly, the hardness is really a measure of the polarizability of the partner atom, the transfer of charge to the molybdenum center. Very nice, very nice. But here's our old friend, molybdenum sulfide. And now, I did this before, really, you know, coming from England, I thought, oh dear, I've got two choices. I can search the literature and find better data that shifts it up here. Or I can say, oh dear, we've got a volcano curve. And the optimum, you see the problem. So we're still working on that. But this is how the kind of patterns generate thoughts. I'm now terribly interested in MOS2 as a CO conversion catalyst. Well, let's now get boring and go into the real world. Here are moly catalysts. These are the kind of workhorse large volume catalysts. Selective oxidation, bismuth moly, propene to acrylonitrile. Always say to my students, always write a balanced chemical equation and you'll be surprised. So I put the oxygen in and the water and the ammonia, methanol oxidation, iron molybdate, and our old friend, the cobalt moly hydrodesulfurization catalysts. These are still, I mean, I talked about molybdenum catalysts old and new. These are old and still, I think, the major volume molybdenum catalysts. Well, what do these catalysts do? What's happening at the active site? And this is really a summary of the chemistry that's going on. From the point of view, I think, of very much of the inorganic chemist, coordination chemistry, reactant binding, product dissociation, acid-base chemistry, protons or whatever, on the partner atom of the molybdenum. The point I want to keep bringing out is the importance of the partner atom, oxygen, sulfur, carbon, nitrogen, in the catalytic chemistry. I mean, the molybdenum, in a sense, is providing opportunities for chemistry at X. So there are various processes. Then the redox chemistry, most cases cycling between moly-4 and moly-6. And that's true of the heterogeneous catalysts, and it's true of the moly enzymes. So, in terms of the fourth dimension, then, we're looking at reactivity, and to summarise, our concerns are proton transfer, electron transfer, atom transfer, remembering that the last atom we want running around on our moly catalyst is oxygen, because that's simply going to chew up our reactants, and whereas we want selective oxidation. Substrate binding and activation, question mark. We always assume that the role of the catalyst is to bind and activate the molecule we're interested in, thiophene, for example. Not sure about this. Maybe much more important to activate the small molecules, hydrogen, nitrogen, and oxygen. So we're providing a supply of highly reactive atoms. And I shall try and develop that theme. Now, let me, as a little aside, show how... Sorry, you shouldn't see the top bit of that. I know this is very irritating, because we all think, now what's he hiding? But it's an old slide. Oh, sorry, and this is a rather curious reference in Journal of Inorganic Biochemistry, because I wrote a rather interesting review on comparing molybdenum in enzymes and heterogeneous catalysts. That's why this keeps reappearing. But I thought we could present desulfurization in a slightly different way, which then connects up with molybdenum oxygen chemistry. we can think of the sulfur molecule as simply having the function of inserting sulfur into activated hydrogen. So here's the sulfur goes into activated hydrogen via binding to molybdenum, and we'll see that this concept is actually quite useful in rationalising a lot of the chemistry. So the sulfur compounds are simply oxidising agents. That's really all they are. Now, quick return to the real world. What molybdenum compounds are being used as catalysts? Well, the US Patent Office has a very useful database. I suppose you've got to put in the right search terms. Last 20 years, then the number of patents, we see oxide still dominates. Quite know what happened here. Sulfide, yes. Carbide, well, you know, oscillating a bit. Carbide's becoming a bit more popular, and you know, nitride's down here. And we ought to start doing something about these, don't you think? So that's the real world of people who want to develop commercial catalysts or possibly reveal information with which they wish to hide what they're really doing or mislead their competitors. However, so I'm not naive. Right then. Oh, I've got to do this. Here's another very boring list. And of molybdenum catalyst, our old friend, the cobalt molysulfide, the selective oxidation. Then there's an interest in activation of propene to propene, for example. Curious work on the photooxidation of propane over molysilica. Acidic properties in hydrocracking. Add a pinch of vanadium and you go on to acrylic acid. Heteropolyacids with their acid function, which will hydrate isobutene to tertiary butanol. Supported peroxo complexes. Propene epoxidation of hydroperoxides, and so on. Those, as far as I can discover, are the main uses of moly catalysts. But let's not forget the moly enzymes. Rather amusing little enzyme is carbon monoxide dehydrogenase, which is the ambient conditions water-gas shift reaction, and the catalyst is an iron, molybdenum, sulfur, selenium cluster. The oxidoreductases, these are all molybdenum oxosulfur compounds which catalyze these reactions, xanthine, sulfite, nitrate, and the famous nitrogenase, which takes us right down to the lower oxidation states as an iron, molybdenum, sulfur cluster. One of the things that from time to time we've tried to do and thought of doing is how can we exploit this ambient molybdenum chemistry? And I shall conclude on that theme. Let me now go to carbon. Well, you know, there's the old story that you add a pinch of carbon to moly, and what you do is you move it 2 places to the right in the periodic table to ruthenium. I don't know that that's very helpful, or we even need to think in those terms. The carbon, the relatively low electronegativity, softness of the carbon, simply moving electrons onto the molybdenum. So it's a better pi donor in, for example, reactions of carbon monoxide. Now, Mark Ledoux is going to talk about molybdenum carbon, and I don't really want to steal his thunder. And I'd be very unwise to do that, I think. But I thought I ought to mention these. You'll see, I'm going, as I say to students, if you want to organise your data, information, go through the periodic table. So we're going to carbon, nitrogen, oxygen, and sulfur. This is what's happening. And I want to pick out 1 or 2 points for, in each example. Now, so a point I want to make about molybdenum carbides is that you can take the pure carbide, and this is now actually in the process of being manufactured by the Climax people. But you can also generate carbided species by carbiding molybdenum on alumina, and you can also make carbided species from molybdenum carbon catalysts. Some years ago, we looked at molybdenum carbon catalysts, and you could, by XRD, demonstrate that those catalysts which had got molybdenum carbide were really quite active in CO conversion and in reforming reactions. I want to pick out one example to illustrate my theme, and that is benzene hydrogenation. This is in the literature. The point being made there is that we plot the rate of benzene hydrogenation, some kind of curious way of doing it, and against the density of sites determined by CO absorption. I think we've had one or two papers on CO absorption on molycarbon catalysts. Now, I'm showing this for this reason, that as we increase the degree of carburation of the molybdenum, as shown by the uptake of carbon monoxide, so we increase the benzene hydrogenation rate. But not only that, it's not only the number of sites that are increasing, it is, as they say, the quality of the sites. So the curve begins to take off. In other words, as we give molybdenum more and more and more carbon partners, we transfer more electron density of the molybdenum, and it becomes better at this kind of metallic type catalysis. I think in some ways the theoretical challenge is to understand the connection. So we go on to, rapidly on to nitrogen. You pick up from the literature various examples of molybdenum nitride and nitride, obviously ammonia synthesis, and there are a number of recent examples. Also reactions like butene isomerization, and obviously hydrodenitrogenation, because that is removing nitrogen from a nitrogen compound. And I'm going to focus on one or two examples. Well, let's look at ammonia synthesis. You know, there's been work on and off for many years on ammonia synthesis over molycatalysts. Again, you plot against the periodic group, and this is the metals on active carbon promoted by potassium, and the outstanding ruthenium osmium catalyst. We can't compete with ruthenium and osmium, except I should say on price. So you know, let's not forget the economics. And when you look, and molybdenum is not too bad. It's not too bad really. It's on the same level as iron, and iron, you know, is a bulk ammonia synthesis catalyst. However, it turns out there's a lot more to be said for molybdenum than one might have expected from that plot. Now, there are two groups who have recently done some fascinating work on cesium, molybdenum, cobalt nitrides, the Japanese group and the Totso group. In fact, I was talking to Dr. Jakobsen, and he said, don't bother about the nitrogen, you know, it's not what matters in these structures. These ternary nitrides are made by reacting cobalt molybdate with ammonia in hydrogen nitrogen, or impregnating molynitride with cobalt nitrate and heating in ammonia. And to those of us who are practiced in molybdenum chemistry, this is extraordinarily like the preparation of a cobalt molybdenum sulfide catalyst. So, I think it just happened I picked up the Japanese paper, so that's actually the plot I've got. This is actually extraordinarily interesting, and I'm sure there's a lot of work going on in the Totso group and in the Japanese group, where you plot the rate of ammonia synthesis against the pressure. Well, you know, I don't think we've got molynitride would come down round about here. Cobalt molynitride, well, you know, and you throw in, you just slosh in cesium nitrate or whatever, well, And then you think, well, you know, perhaps the amount actually matters. And when you put in 2%, just a pinch of cesium, the whole thing takes off, and you get a highly active, an ammonia synthesis catalyst that's much more active than the iron catalyst. Scientifically, I mean, that's quite fascinating because of the demands made on this kind of catalyst to split N2, split H2, bring them together. Commercial possibilities, I have no idea, but I mean, the challenge to the Haber catalyst is cost, I imagine, to reduce the temperature, reduce the pressure at which you do the synthesis. Bearing in mind, moly enzymes do it under ambient conditions. So, while we're talking about ammonia synthesis, let me mention the moly enzymes as an iron moly sulfur cluster, ambient conditions, and the reaction gives ammonium ions and hydrogen. Have we thought of nitrogenase as a source of hydrogen for our fuel cells? I ask myself. That's much more to the point than the synthesis of ammonium ions. Who wants a dilute solution of ammonium ions? That's not the point. I should make the point that the rate determining step is the protonation of bound N2 molecules. Great contrast with the heterogeneous catalysis where the rate determining step is splitting the N2 molecule. Curiosity led me to compare the rates of ammonia synthesis in the enzymatic chemistry and in the heterogeneous catalysis. It's a bit difficult to compare them. As far as I can see, the enzyme is pretty good. 2 ammonias per second per cycle. Iron synthesis, I don't know, under these extreme conditions, 1 ammonia per second per cycle. Ruthenium carbon 0.2. Poor old unpromoted molybdenum right down at 10 to the minus 4. So you've got to know what to add and how to add it if you want to make the most of your moly compounds. And we can break it down into a series of proton and electron transfers where the source of the oxygen is oxide of the lattice. And the catalyst has then got to accommodate protons, electrons, and dispose of vacancies. And the protons go to the O2 minus. So the critical thing is that the O2 minus should be basic, that it should be nucleophilic, it should bind protons. And this is the kind of work that the Harvard group have very much aspect of sorted out. Just let me refer to this work here. That is how selective oxidation occurs. This is again work from the Harvard group and a review by Barbara. Well, I know Barbara well. I'm sorry, I'm not very good at this. But I do apologise. I'm sorry. I'm sure Mitchell is difficult for. Look, I'm sorry. That's awful. I apologise. But anyway, the critical step is CH bond scission, and what I think is now clear is that both fragments of the CH bond bind to oxygens, forming an alkoxy species or an OH, and the metal atom is kind of sitting in the middle. And what is the metal atom doing? It's controlling the chemistry of the oxides. If it provides basic oxides, that facilitates this chemistry. And then you've got various electrons to sort out and so on. So this is the picture I drew, or my computer drew, of the Krakow work. So you've got your propene sitting between a metal atom but joined to these 2 oxygens. If that's cobalt, you do the first CH bond breaking. Molybdenum will do it, but not very well. That's because these oxygens are really rather nicely basic. So that's really what's happening in this catalyst. One other point, and it's this, shown on this little overhead here. Long, long ago in the middle, if not the dark ages, we were very interested in how these oxo-molybdenum species react with hydrogen sulfide as a means of making molysulfur complexes. What we found was that the reactive oxygen is the bridging oxygen, whereas most people think, you know, you've got this kind of dangling oxygen. It's rather like the dangling sulfur that we saw yesterday in a cobalt moly catalyst. But there's a multiple bond. And the reactive oxygen in the chemistry and in the catalysis is the bridging oxygen. So, in a sense, the chemistry and the catalysis have now come full cycle. Right, how could I not mention sulfide catalysts? I do this with a certain temerity. However, let's plunge in. We all know. Thiophene desulfurization, promoted by cobalt. Now, we did with Collis Scott, again, some years ago, we actually looked at the activation energy. And what we found to our surprise was that although cobalt enhances the activity, it seems to increase the activation energy of the this is the effective activation energy. I thought it was very odd. And we looked in the literature, and as far as I can discover from the literature, the effect of the promoter is to increase the activation energy. So, we must look at the pre-exponential term in the Arrhenius equation. There is a compensation effect. The active phase, well, it was fortunate that I read, or that we received in England, the latest Topso paper, the STM paper, and that I've got a colour scanner, so that in due course that will appear. How does the reactant react with the catalyst? Well, one of the techniques we've used is inelastic neutron scattering. Now, this might seem a bit exotic, but essentially you get an energy loss spectrum, you get the full vibrational spectrum, no selection rules, and the neutrons will go through steel. So you don't need ultra-high vacuum, and you actually need 50 grams of catalyst, no problem about representative sample, and you see the hydrogen motion strongly emphasized, really see the hydrogen, and you don't have a problem with the background, with the container. Brilliant technique. Why doesn't everybody use it? Oh, that's another story. We looked at thiophene on cobalt, on molysulfide, cobalt molysulfide catalysts. What we saw was that the motions being affected were the out-of-plane motions of the hydrogen. No doubt about this. But they were changed much less than for thiophene in thiophene complexes. The interaction is clearly very weak. And we thought the thiophene is on the basal plane, and I'll show a little picture of what's happening there. Now, let me show another famous picture. That's, and with due acknowledgement to Henrik and his colleagues. But people get engaged in controversy about whether this is true or not, about the exafs, you name it. I'm not interested, well, sorry, I am interested, but what I want to do is draw attention to a particular feature of the STM that was in the paper, and that is, I think, Henry, you'll correct me if I misunderstood the point, but that you introduce cobalt and you then enhance the negative charge, you enhance the electron density on the sulfur. Now, this is right, isn't it? Yeah, good, good. I didn't want to proceed unless I've got this right. Now, that is extraordinarily interesting, you see, in terms of the fourth dimension in catalysis, because cobalt is doing the same to the molysulfide that it does to molyoxide in a cobalt molybdenate catalyst. It is fine-tuning the chemistry of a partner atom. Obviously, it's making the sulfur more attractive to the proton, making it more basic, more nucleophilic. You know, the patterns are beginning to fall into place. Anyway, I was pleased to have read that paper before travelling across the Atlantic. Well, time's pressing on. Just let me show you our neutron scattering. That is thiophene, and people look at XFs and they say, I can't see any difference. And what I can say with neutron scattering is, you know, you really ain't seen nothing yet, just watch my lips. Because when we look at that is pure thiophene, when we look at thiophene on a surface, then, well, it broadens out, you lose some of the features, but you see, because there are no selection rules, it's easy to calculate the spectrum, and we can calculate the spectra and find out what the thiophene is doing by simulating the spectrum. This is actually published. And what we then find is that we can simulate the observed spectrum by having 90% parallel thiophene and 10% thiophene upright. Best of all possible worlds. We have disposed of the argument, is thiophene parallel or perpendicular? It's both. You know, that's very, very satisfying. The interaction is weak. It really is weak. Now, okay, we've been criticised. People say, but you're actually not seeing the very small quantity of reactive thiophene. All you're seeing are spectator molecules. I'm sorry, you know, what can one say? If you can't see it, I mean, what is reality? That's a kind of philosophical problem. I mean, is it there? Anyway, so this is our picture, which I have to say predated the STM pictures. All the INS evidence is that thiophene is interacting weakly with the molysulfide basal plane, moving across to the active site. Now, when I saw the STM picture yesterday, there was one quickly flashed up with thiophene, and I wasn't sure whether it showed thiophene like that. If it does, I think this is, you know. How's time coming on? 5 minutes, all right.
Well, actually about 2. If you want to.
So this is the chemistry. Thiophene on the surface, and the critical thing is to supply our thiophene with hydrogen atoms. Problem is not thiophene. Problem is hydrogen. H2 will not react with anything. H2 won't react with thiophene, it won't react with coordinated thiophene, but as soon as you generate H atoms, they will react with anything. And this is what the catalysis is about, I think. And this is what the compensation effects are about. And I've almost, just let me show what I mean. Compensation effect is telling us that what matters is the reaction probability if we plot the pre-exponential against the activation energy. That's for a series of promoted catalysts. Fortunately, it was published in a journal which is not, you know, one of the that everybody kind of consults regularly, but that was conference proceedings. But you look back on the old work of Kemble all those years ago, where he knew how to do kinetics. He really knew how to do kinetics. And you've got the same kind of compensation effect in sulfide catalysts. And this is, how more fundamental can you be than the hydrogen-deuterium reaction? And there it is. And I think what we're seeing there is the need of hydrogen atoms to get to be supplied to the active site. And they are determining the reaction probability. So, one more minute, I think. Let me just mention, and then I'll kind of fade out, how we're trying to exploit the enzyme chemistry. What you can do, you can create, this is a moly dithiocarbonate complex, moly with sulfur ligands, and you can put it inside a zeolite. So you can there create a reaction space, kind of ship in bottle, which everybody does nowadays. And you can calculate the structures that derive from, as it were, compressing the dithiocarbonate in the zeolite cavity. What you find is that it makes these two complexes, a dioxomolybdenum and monoxomolybdenum, it brings them closer together structurally. And that's fascinating because it's going to lower the activation energy for the oxygen transfer reaction. So we're trying to exploit that kind of chemistry. So I think, what else do I have to say? Oh, one final point, and that is, of course, if we're going to exploit these catalysts, we've got to learn how to manufacture them. We've got to learn how to render them stable in a mechanical sense, mechanically stable, form them into pellets of the right shape and so on. So I think there's a whole area out there that the kind of academic content must not neglect. So what's the take-home message? Well, think molybdenum. Thank you very much. Think in 4 dimensions. It's reactivity that's the challenge. And calculate, we've done some calculations. We did density functional theory on we found that sulfur became a bit more negative with cobalt, but the molybdenum was negative and I didn't like that very much. So I said to the student, I don't know. Anyway, so I think the calculations are very important, but I don't think we can calculate everything. It's very important to select critical examples and push to the limit so that we know that the calculation is right. Finally, you know, let's be dynamic. Thank you very much.
Thank you, Philip, for a very nice presentation. As I was listening to you, this is for my American colleagues, I'm sure, that thank goodness Philip did not enter politics, or we may have a new meaning of what is really means. Anyway, we may have time for about one question. Anyone got any questions? Or you can catch Philip, he'll be around the meeting, you know, the rest of today.